So today we have an amazing topic and an amazing speaker. We have Dr. Neil Gunter, who's going to talk about a very interesting topic. And during the talk about the topic, he'll talk about the history, journey, and how quantum computing came into what it is today. Um, this is about me. I am a director at a company called Kaiser Permanente in California. My focus is on digital twins and machine learning predominantly these days. I have been the author of a couple of books now, Medical Image Processing with Deep Learning, which is probably old right now, and then Intelligent Governance. I have my volunteer with me. She is going to join a few minutes late. She's very interested in today's talk. She is focused on quantum computing as well, but she's a middle schooler, so she'll try her best to understand. That's what she said, and learn as much as she can. And then she'll write down her questions. So Dr. Gunter expects questions,
That's
at least
fine.
from one kid and later on in the day.
I'm going to direct my talk at her so that she does understand.
Okay, perfect, perfect. Um, So, Dr. Neil Gunter, it's an amazing privilege for me to host you. I mean, when I received your ping, I was a little surprised. I was like, wow. But Dr. Neil Gunter is someone who has the opportunity to uh, work with indirectly under the student of Dirac himself. Um, and Dr. Neil Gantar had the privilege to also see actually Dirac, not Sommerfeld. Um, so he is one of the people who has seen everything right from the beginning. His career is spanning over last 40 years. He has a PhD in theoretical physics. And it will be an amazing talk. I had the privilege of speaking with him for like an half an hour. Like we wanted to talk for 5-10 minutes, and I think we ended up half an hour or 45 minutes. And that's because I had a hard stop that day, but it was an amazing discussion. So I'm sure everybody's gonna have a nice time talking to you. With that, Dr. Gunter, I'm gonna pass it on to you for you to share your screen, and then we'll take it from there.
Okay, I think it's right. So, is that working?
Yes.
Cool. Okay, so I'm not quite as old as the beginning of quantum mechanics, but I understand what you mean.
I'm sorry for making it sound like that, Dr.
I read a lot. So I would also like to thank you, Tapash, for accepting my proposal, because it's actually been quite inspirational for me to pull this subject together in an even more coherent way, I hope, and a more refined way than what I originally had in mind. And so where we've ended up, much to my amazement as anybody else's, we really have three sections or three topics or subtopics that have sort of emerged out of putting these slides together. And we're only going to deal with one of them today. And the other two we'll deal with in later sessions or another session, however this works out. So the focus today is on a new explanation of the old paradox, which is what I'm going to explain, the Dirac-Sommerfeld paradox. And although this is really, quite an intricate topic from the point of view of quantum mechanics, I'm not going to go into the details of the math and all of that stuff. I'm going to assume you had some at least glancing blow with quantum mechanics. You ought to if you're doing quantum computers. Obviously, the name Dirac pops up all the time in terms of, the Ket notation and so on and so forth that's used for quantum circuit diagrams. And I'll come to all that in the third part. But what I'm going to do is start with the original paradox, and then I'm going to thread the discussion through topic number 2, which is, could Sommerfeld have discovered quantum mechanics version 2, I'm going to call it. I just invented this notation yesterday, actually. So I'll explain what I mean by all these different versions, and then we'll consider that from a point of view which, as far as I know, nobody else has ever considered before. It's quite an interesting question to examine. And that leads us to topic 3, which is quantum mechanics version 3, which I'll explain, that underpins modern quantum computing. So this is really a personal journey or a personal pathway, starting with this Dirac-Sommerfeld paradox, which was laid on me by my master's thesis advisor at the time. And it's my thesis advisor who was one of Dirac's very few research students. There's a reason he had very few research students. Nobody wanted to work with him because it was too emotionally difficult, because Dirac never really said anything. So you may have read that he had a sort of a taciturn nature. Man, it's way different from that. It's psychologically very disturbing. And if we had time towards the end, not today, but towards the end, I can give you some personal accounts of my actual interaction with Dirac when he came to Australia. So let me move on to this topic. So I want to thank Tapash for helping me to pull all this together. I've now reached the point where I think I could safely say this is actually worth peer-reviewed publication, which wasn't on my mind when I first approached Tapash, but his excitement, his enthusiasm in response to our discussion we had the other day, and me trying to pull these slides together in a coherent way so that everybody that's in the audience can understand at least most of it, has really made a big difference for me. So I'm very appreciative of that. All right, so I just mentioned my master's thesis advisor. So I'm in Melbourne at this point, Melbourne, Australia, and I'm doing my master's thesis in applied mathematics. It's really theoretical physics, but it was in the applied mathematics department. And in the center there, you can see Professor Eliezer. And Christy Eliezer is actually of Ceylonese origin, but he would be Tamil, I guess, in that sense. And today, of course, it's called Sri Lanka. As I just mentioned, he was one of Dirac's very few students. Dirac only had maybe a handful of students during his time as Lucasian Professor of Mathematics at Cambridge University, which is the same chair that Isaac Newton held originally, and of course, more recently, Stephen Hawking. So Eliezer was Dirac's student, I think, maybe in the 1940s or thereabouts. And he was the only person really worth working with as far as I was concerned. And so here he is, and you'll see him later with Dirac. That's me on the left, in case it's not obvious. And there's the thesis. My thesis that we're talking about was on dynamical symmetries. And Eliezer was my advisor for that. So I've shown this in collection with some other books that I've used along the way of putting these slides together, but also along the way of revisiting this paradox, because it was Professor Eliezer that first told me about the Dirac-Sommerfeld paradox. And the reason he did that was because we had lots of discussions in his office from time to time, but he mentioned that in particular because he thought it might be useful as part of my thesis. That was the idea, which was perfectly fine. I didn't actually use it, but he brought it up and we had a discussion. That's the first time I ever heard about the paradox, actually. Having done a first degree in chemistry and a second degree in physics, I had never heard of the paradox until he told it to me. You can find it in some books. Not all books on quantum mechanics mention it. Some do, so it's not that well known even today. But that was my first awareness of that topic. And I'm showing some other books. I'll perhaps pop back to this slide later on, just to remind you of some books if you want to actually look at them yourself. The one that I'm going to be focusing on today is this book in the middle here by Max Born. Very few people seem to know about that book. It's very interesting. I'll explain why shortly. And then later on, we'll be talking about entanglement, something which obviously is critical for modern quantum computing. If you think you understand that topic, or you not sure about how to understand that topic, this book by Azel, I don't know exactly how you pronounce it, name is Turkish. It's just called Entanglement, and there's not really any math in it. So it's a kind of a Stephen Hawking book. Stephen Hawking said if, for every equation he put in his book, he lost 10% of his audience. So he tried to keep math to a minimum. Same here, but it's a very well-written book, very readable, and it's very accurate. And it brings up some things that are not so well known about where entanglement was kicking around for a long time, but people didn't recognize it. And then lastly, in the second section, not today, but when we get to the second section, the inspiration for the way I approach that comes from Feynman's book called QED, which stands for Quantum Electrodynamics, but it's really a book on quantum mechanics, and I highly recommend it in the sense that if you want to avoid all the clutter and all the nonsense about collapsing wave functions and all this stuff that you read, particularly in the context of quantum computing, some of these phrases I really detest. You can get the straight scoop on quantum mechanics from this book. It's very readable, no equations that I can remember, lots of diagrams, and quite well written. I mean, it comes from a series of lectures that Feynman gave in New Zealand, I think towards the end of the 1970s. And of course, he says that I think he was invited, but he said he decided to do these lectures in New Zealand so that if it blew up in his face, nobody would know about it. But I don't think that's true. And actually, I understood fully what he's doing here, because this book down here is another book by Feynman, although he didn't write much of it. By the way, Richard Feynman hated writing, so other people generally had to write stuff. This is the book on path integral, which is another version of quantum mechanics, but it's written by Feynman. L. Hibbs was his Ph.D. student, if I remember correctly, and it's really Hibbs that wrote the book. This is something I'll come back to in the second section when we get there, not today. And this book, frankly speaking, is horrible. I wouldn't recommend it at all unless you're serious about learning how to do path integral calculations. But not only is it's a bit aged these days, but and it is well written from a technical point of view, but it's just horrible to try and understand what's really going on. So the point I'm making here is this is actually the base of the material. This book on QED, written later by Feynman, is if you like, the qualitative expose of what's going on in this book. And so I highly recommend that anybody can understand this. And he simplifies it in such a way that it's quite incredible. And he doesn't pretend to explain quantum mechanics. As he says, basically, we can tell you the rules. We don't know why the rules are the way they are, and we may never know. So I'll come back to this slide maybe from time to time. All right, so the thing we're looking at is paradox. And of course, science from time to time is full of various kinds of paradoxes. I've listed some of them here. The one that we're really focusing on is this one that goes back to the famous paper by Einstein, Podolsky, and Rosen, which is really, I can remember reading that as a student, probably while I was working with Eliezer, I don't recall exactly. And I found it almost impossible to understand, because it's really a lot of philosophical kind of discussion about what is local reality, what is a mixed state. Well, I should say they use those terms without really explaining exactly what they mean, because they're sort of using them as part of the internal explanation anyway. So it's, for a student, I think it's impenetrable. These days we have a much different perspective on it, but at that time when it was written, and much later when I was reading it in its published form, I found it very difficult to read. I mean, I had a degree in chemistry. What on earth do they mean by a mixed state? I never heard of such a thing. And chemists, by the way, you know, they don't deal with one atom or an electron and a proton. They deal with molecules. And they have some very spiffy techniques for dealing with such complicated systems. And amongst all of that, I never heard of such a thing as a mixed state. And I remember having a terrible time trying to figure out what this meant. So, of course, the other thing is that this caused huge conniptions amongst the quantum mechanics community when it was published in 1936. So that's, a few years after Einstein had arrived in the United States from Nazi Germany. This is the paper that he put out. And of course, the reason he did this was because he was not satisfied that quantum mechanics was sitting on a solid foundation from his point of view. And he kept coming up with these, Gedanken experiments, thought experiments, to try and find counterexamples that would shed light on what were the real foundations of quantum mechanics. Now, we know now, I like to say, that Einstein was right, but for the wrong reasons. So, of course, these mixed states that they keep yammering on about in this paper turns out to be something like, an example would be a biphoton state, an entangled state of two photons. The word entanglement is not used in the paper because that was a word that later came from Schrodinger, and it's not in the paper. So, and I don't like that word either, but mixed state was also impenetrable. So, of course, the idea of there being entangled states is really what's going on in this paper. And Einstein constructed the idea of the entangled state to try and challenge the conventional quantum mechanics in the sense of putting it on a more solid foundation. And the conclusion of the paper basically is such entangled states really couldn't exist because they would defy reality, the so-called local reality. Well, of course, that's exactly what they do. So Einstein was right, but for the wrong reasons. He was trying to counter the foundations of quantum mechanics, which turned out to be not such a great idea. But the conceived thought experiment is quite remarkable just in its own right. So ultimately, this is what led to quantum computing. And in case I don't say it in the second section, this is really the underpinning of Feynman focusing in on the need for quantum computers starting around about 1981, so 40 odd years ago. And the reason that he gives, if you read his paper, which is he didn't write, but it's a transcription of the lecture that he gave, it all boils down to this one thing: entanglement, as we would call it today. And what he's talking about the EPR concept, but also the experiments that have been done in the interim, 50 years later, starting in the 1970s and ultimately being proved in the 1980s or so forth. And I think some Nobel Prizes were given for that, if I remember correctly. So Feynman points at this and says that if you try to simulate quantum systems with conventional classical computers, meaning bitwise computers, like the ones we have today, it would not have been able to simulate something like entanglement correctly. So in order, and ultimately what he's saying is that nature is really fundamentally quantum in its behavior. And so that if you want to do things faithfully and accurately, you have to be able to compute things like entanglement. And the only way you can really do that is by having a quantum computer. We'll come back to that in part 3. So other paradoxes such as information paradox and black holes that were generated by Stephen Hawking a long time ago, never fully resolved. Hawking tried to resolve it shortly before he died. I think it's still not 100% settled. The question is, where does information go if things fall into a black hole and the black hole is evaporating? What happened to the information, and so on and so forth? So some people think they have a solution for all this. In mathematics, Russell's paradox created a huge challenge for mathematicians and led ultimately to, I suppose, what we'll call set theory for the non-mathematicians, if you like. And the Russell's paradox is simply imagine a town where there's a barber who shaves every man who doesn't shave himself, which raises a question: what does a barber do? So paradoxes are important. They arise from time to time. Some are more serious than others. And in one way or another, they usually lead to some kind of developments. For example, this guy here says, the borders of paradox is a fruitful place to be when you're trying to explore things. So they can lead to new conclusions. The alternative is, as Feynman says here in his Nobel Prize lecture, sometimes paradox that appears that way at first. When you really look at it closely, the paradox kind of vaporizes. And I think we're looking at that situation here. So I'll come back to that in a minute. All right, so what is the paradox that Eliezer told me about? So let's just pop back for a second and set some context here. So basically, we're going to be talking about the hydrogen atom. And historically, that's also true because it's the simplest system to try and understand. And if we go back to the 1900s, starting really with Planck in 1900 and followed up by Einstein in 1905. Einstein in 1905 proposed that light was composed of quanta. Today we call them photons, particles, in other words. That idea is quite remarkable in its own right, and therefore was not well received in 1905. The problem, of course, is that light, today we think of it as being composed of photons. Back then, the framework would have been the classical framework of Maxwell's electromagnetic theory, which was, a crowning success in its own right, because it explained the interconnections between electricity and magnetism on the one hand. But when Maxwell finally was able to complete the differential equations with the fourth differential equation, what we call Maxwell's equations today, well, four equations, I say four equations, I mean four vector equations, it's really more complicated than that. And don't bother trying to read Maxwell's equations in the original paper because it's really mind-bending, because every component is in there, it's very difficult to follow. And nonetheless, the other critical conclusion is that there's a constant in the differential equations, C, the letter C. And it turns out that the value of that parameter in the equations is very close to the speed of light. In fact, today now we know identically it is the speed of light. And that was the framework in the 1900s. But the problem is that if you think about, so we're going to talk about hydrogen atoms because it's the simplest atom, as I'll show you in a minute, but it's a gas. And obviously the sun is made of hydrogen because it's essentially a continuous hydrogen bomb, converting hydrogen into helium. And if you look at sunlight, not directly, not advisable, but if you take a spectrum or you look at a rainbow, that the light that's coming from the rainbow is acting as a, the diffractions acts as a prism and breaks the light up into its components, the colors of the rainbow that Newton originally identified in the mid-1600s or so. But that's a continuous spectrum. The colors sort of blend through one another. On the other hand, if you take hydrogen gas alone and put it into a vacuum tube and send an electric current through it, it will also emit light, but only of one color, roughly a very, very faint bluish color. And then if you put that through a prism, what you see is not this continuous spectrum of light, but bands, discrete bands of light. And the question at the time was, what on earth is going on? Because we really see a continuous spectrum in general. But when we look at hydrogen in its own right, alone, we see these bands. Of course, what's going on in the sun is a total mess. It's a bomb. So we're not just looking at hydrogen in the sun, it's converting it to helium. The whole thing's at this humongous temperature. So we've got plasma, magnetic effects, and so on and so forth. And this tends to spread the spectrum out because there's lots of things going on. We're not looking at the pure hydrogen spectrum in the rainbow. It's in there, but it's only one minor component. You wouldn't be able to see it anyway. But if we separate out the hydrogen specifically, then we do see these discrete spectra. That's a problem because if we use Newtonian mechanics or Maxwell's theory in a sense, you can't get there. These discrete lines do not appear because both Newtonian mechanics and Maxwell's electrodynamics are a continuous mathematical model, both of them. And therefore, it's very difficult to understand how do you get these discrete lines from this such continuous types of models. And so on the right-hand side here, I've drawn the spectrum out because I've just shown part of it here on the left. But it actually sits in bands, and you see these lines, they kind of bunch up together and then they begin to spread out. Then you go to another area of the spectrum and they bunch up again and then they spread out. This spreading, bunching effect was noticed very early on, and ultimately, I think it was Balmer wrote down a formula, and it's an empirical formula that explained how this bunching in the spectrum occurs. If you identify the number of the line by this lowercase letter n, there's two of them. I won't get into all of that, just separates the different groups. But basically, the important point is that the energy or the frequency of the light in each of the bands is inversely proportional to the square of the number of the line in the spectrum, if you enumerate them in an appropriate way. So this is the problem. How on earth can you get there? You can't get there from Newton and you can't get there from Maxwell. This was reluctantly, physicists began to realize this was not going to happen. Enter Niels Bohr on the right of this particular photograph. And on the left, we have the culprit in all of this, which is Arnold Sommerfeld. Arnold Sommerfeld, by the way, was Heisenberg's Ph.D. advisor, in case I forget to say it later. So Sommerfeld on the left, Bohr on the right. And in 1913, Bohr had already proposed a model which gave the correct line spectra, at least to first order. And the idea is that the hydrogen atom is not the original plum pudding model, because somehow the atom has to be neutral, but if it's composed of electrons and protons, how do you get these charges to cancel out? The original conception was that they're all lumped together like in raisins or something in a plum pudding. So it was called the plum pudding model. But then Rutherford showed that that's not right, that if you try to scatter alpha particles of gold atoms in particular, sometimes they'll ricochet right back at your alpha gun, so to speak. The point being that other times the alpha particles would go straight through the foil. So point being that, indeed, as we understand today, the atoms are actually composed mostly of space, not plum pudding. So Bohr's conception, following on from that data, actually, because Bohr was actually at one point had gone to the Cavendish lab at Cambridge and was, working with Rutherford in some way. And it's during that time, as far as I can recall, that he had this idea for a planetary model of the atom. When I say atom, I just mean hydrogen atom here. Meaning that the proton would act like the sun, attracting a planetary electron. It's only a single electron. The hydrogen gas is just a proton with an electron in it. And that the electron is orbiting just like a planet in that sense, by analogy, not directly, obviously. The difference is, of course, gravity has nothing to do with it here. So the gravitational force of Newton, the 1/r² law, is replaced by the Coulomb electrostatic interaction, which is also inverse square law, interestingly enough. By the way, the scale factor, just in case you don't know, the scale factor that separates the electrostatic force from the gravitational force is 10 to the power 40. So it's 1 with 40 zeros after it, meaning the electrostatic force is 10 to the 40 times stronger than the gravitational force. So, but from the mathematical point of view, it's almost an identical kind of an equation, except that the mass charge, such as the Earth being attracted to the sun, is replaced by the electric charge. So that's interesting because there's the Maxwell component, if you like, of the theory, and the planetary model is the Newtonian component of the theory. So in some sense, Bohr is managing in some way to combine Newtonian mechanics and Maxwell electrostatics together in the context of the atom, which was one of the confounding problems. Well, that's well and good, except for the fact that if the electron is orbiting in the same sense that the Earth orbits the sun, there's a problem, there's an additional problem which we don't have in a gravitational situation. That is that the electrostatic charges are charged. The mass charge only has one charge, the mass density. So it doesn't have any sign associated with it, or it's a plus sign. Whereas an electric charge can be the positive or negative. Worse than that, Maxwell's equations tell us that if you have an orbiting charge, in order to make it go in a circle, just like the space station going around the Earth every 90 minutes, it's attracted by a force. What's the force? The Coulomb force, inverse square electrostatic force attracted towards the proton. But the circular motion means that it's also rotating at the same time as being attracted in such a way that, in a sense, the electron is falling infinitely into the proton, never gets there because it has enough tangential velocity in this model to avoid being pulled in, just like the space station doesn't fall to the Earth. So for the space station, it's fine. For the electron, there's an additional problem that Maxwell tells us about, which is that means that the electron is being accelerated towards the center of the atom, the proton. Any accelerated charge radiates, meaning it emits electromagnetic radiation. That's a problem because obviously the electron is being accelerated. It's a central force accelerating it, centrifugal force, if you like. And therefore it must radiate. If it radiates, it will lose energy and simply spiral immediately into the proton, and all matter would collapse. Obviously, that doesn't seem to be the case. I just looked out the window. We're still here. So this is the problem. What are you going to do about it? Well, physicists, often aren't daunted by such things. So what Bohr came up with was, well, I'm just going to make a rule. And in a way, this is the beginning of why nobody understands quantum mechanics, because there is no graceful way to explain that other than imposing a rule. And in 1913, this looks very ad hoc, which it is. But it turns out even decades later, as Feynman says in his QED book, don't try to figure out why the rules are the way they are. We know the rules, we don't know why they are. So this was completely ad hoc at the time, but in the spirit of Planck, 1900, saying that energy was quantized in some general sense as a hypothesis, and Einstein running with it in 1905 to take that even further and say all light is composed of photons. Just, by the way, in case you don't understand the impact of that, light was understood to be waves, both from the point of view of producing interference, just like water waves, and also from the point of view of Maxwell's electromagnetic theory. The electromagnetic equations are electrodynamic equations of a wave motion. It's complicated because you've got the two fields, the electric field and the magnetic field, but the point is that the Maxwell tells us these are all related. They're just two aspects of the same thing, if you like, the electromagnetic fields. And the fields, the solutions to Maxwell's equations are in general wave solutions. So that the radio waves that come to you from a radio station, if you listen to it that way, are electromagnetic radiation, making the electrons in the antenna of your radio move up and down in sympathy with their frequency, and with the correct circuit that's tuned to that station, so on and so forth, you can convert it back to sound waves. Quite remarkable. Anyway, the point is that light was well understood to be waves. And here's Einstein in 1905 saying, well, in order to understand things like the photoelectric effect is when you go to the grocery store and the doors open automatically, that's the photoelectric effect. There's infrared radiation that you can't see, it's bouncing off you. The photons are impacting the detector that get converted to electrons, drive the motor that opens the door. That's the photoelectric effect. So you're very familiar with it. And Einstein's saying on that basis that light is made of photons, particles. And this caused huge ruction in the physics community because people really couldn't accept that light was photons. Even today, it's still, I would say, somewhat controversial. I don't have a problem with it, but a lot of physicists do. Anyway, the upshot of all of this is that if you create this planetary model, which Bohr did in 1913, and you solve it with this ad hoc rule that says the electron stays in its orbit, and when it's in a given orbit, of which there can be different ones, as I'll show you more later, it doesn't radiate. It's only when it makes a transition from a lower orbit to a higher orbit and then falls back again that it emits radiation as photons. It's not important that it's photons, but of course today we would say that it's photons. So with this ad hoc rule attached to a Newtonian planetary model where gravity is replaced by the Coulomb force, you get this result for the energy. Notice that it's 1 over n squared. Remember the Balmer formula here? And so therefore this works. By the way, just over here, I'm showing you the potential energy is that curve. So this is the x-axis at 0, and then we go in a negative direction because it's a binding energy. The electron is bound to the proton because they're a different charge. And there's the first Bohr orbit, E1, or n, and that corresponds to n equals 1, and that gives you the binding energy of 13.6 electron volts, which you can measure from gas discharge tubes. So this was completely well known. And then if we go up here, for example, there's there, E2, that's the second orbit that's allowed under the constraint that Bohr has imposed. And then you see, because it's 1 over n squared or 1 over r squared potential, see how the distance between the orbits now begins to close up, just as you saw back here. Look at this kind of thing, this grouping, this clustering is coming from basically the Coulomb potential and the corresponding discrete energy levels. The electron's not allowed to be in between these levels, only at one level or another, but it can transition between the levels, and that's when the radiation is emitted. Otherwise, no radiation is emitted, which completely contradicts Maxwell. Nonetheless, this works. And as Einstein remarked, this is such a remarkable idea that Einstein referred to it as Bohr could only have come up with this by understanding the music of the spheres, which is a reference to Pythagoras, actually ancient Greeks. So this, I mean, Einstein didn't think of this, it was Bohr, and it really is truly a remarkable result. Now, by the way, I've got a picture here. This is a picture of a hydrogen atom, a real hydrogen atom. This is not a photograph, but it is an image of the hydrogen atom. So by some very clever techniques, you can create an image. Basically, what's happening is they're forcing it to emit photons in such a way that when you capture them and store them in what's called a storage scope, this is what it produces. So it is producing an image. This is an image of a hydrogen atom, only been done in the last, I don't know, 5 or 10 years or something. I don't remember the date. And you can see, remarkably, look, you can't call these orbits in the Newtonian sense, but there's certainly a lot of circular stuff going on. So this idea is not as crazy as it might seem. Now, the problem is it was well recognized, already known, because a lot of experiments have been done measuring the spectral lines of hydrogen in particular. It's relatively easy to do. However, some of the things require very high resolution microscopes to see the details of the line spectra. So they're not necessarily individual lines. For example, this red line is actually a doublet, but you need a magnification of about 1000 to see it. So the Bohr model does not account for that. On the other hand, there's absolutely no shame in that, because this is how physics works typically. You know, you don't construct a model that contains everything, otherwise we'd all be out of a job. So you start with various levels of approximation, and then you try to add more detail in, and then sometimes you've got to change the entire context, and radical paradigm shifts occur from time to time. And the gap that's associated with this so-called fine structure of the spectrum is associated with this constant, which is a very famous constant in physics if you haven't seen it before. It's the originally called the fine structure constant when it was introduced by Sommerfeld in 1916. Today, I think of it as the electromagnetic coupling constant, how strong the photon couples to an electron. Photons don't interact with photons. Photons only interact with electrons. And this is the magnitude of that coupling. And it's a famous number, 1 over 137. I think it was Eddington at one point, very early on, back in the 1900s, tried to propose a theory of why the fine structure constant had the value, not 1 over 137, but at that time, it wasn't measured as accurately as we have today. It was more like 136 as an approximation. And so Eddington came up with this idea about 16 by 16 matrices and so on and so forth. And around the time he published this paper, the number was refined to be 137. So that idea didn't gain any traction. So the question is, what causes this splitting? I'm trying to get a move on here because we're only have an hour, right? So the Bohr model does not obey the rules of relativity. The other paper, or one of the other papers that Einstein published in 1905. So this is what Sommerfeld did, tried to add in corrections. And as a consequence of that, this means, for example, that the orbits aren't necessarily circular. They can be elliptical. Planetary orbits also can be elliptical without, special theory of relativity, but they're elliptical under Newtonian theory. But this elliptical behavior is coming from this electromagnetic coupling constant. This is not a gravity system. This is an electromagnetic system, not to be confused. So the key thing to understand is that when you have ellipses, what Sommerfeld did was he identified two quantum numbers. So the original Bohr model, just going back here for a second, that introduces n. N is the energy levels. The principal quantum number gives you the initial energy levels that are possible. Now, of course, we're going to talk about splitting these energy levels in some sense. So Sommerfeld introduces a new quantum number, which is related to this elliptical shape of the orbit. And indeed, what's called the aspect ratio of the ellipse. It's kind of like, it's related to the eccentricity, but that's not what he used as a mathematical form. So he was looking at the ratio of the major axis to the minor axis, which is not quite the eccentricity, but it's related, obviously. And he makes this ratio equal to n, which is the Bohr n, principal quantum number, and he introduces a new quantum number, k. And then he solves the equations that belong to the relativistic version of the Bohr model and comes up with this formula. This is the formula from Bohr. Now we get this new formula from Sommerfeld. So there's alpha, so there's the electromagnetic coupling constant, m times c squared, mc squared, there's the Einstein relation in there, and so on and so forth. So we have now the Bohr integers, the quantum numbers. K is this new quantum number. I'll just call it sometimes the eccentricity quantum number, just for a label. And it has these values. So 1 up to n, what you choose your energy level, principal level, and then k ranges as an integer between 1 and whatever that level is. When they're equal, then the whole system collapses back to the Bohr model, which is good. In addition, of course, you get other complications because the angular momentum is conserved in the Bohr model. Any spherically symmetric system will have the angular momentum conserved, meaning that it doesn't change in time. But in addition, as Born explains in his book, I mentioned that book in the middle of the stack there. This is from Max Born's book. He shows this rosette motion. So the angular momentum vector forces the orbit to be in a plane. Otherwise, the vector would in some sense be wobbling, but it's not. It's fixed. It doesn't change in time. Therefore, the orbit has to be in a plane. And there's another vector, not so well known, called the Runge-Lenz vector, which is in the direction of the plane. And it points in one direction, and that prevents the orbit from rotating in any sense. So when the Runge-Lenz vector R is conserved, you can't get this motion. When you have a relativistically invariant potential, however, that Runge-Lenz vector is not conserved anymore, and so the orbit begins to precess, it's called. So what that means is the orbit doesn't quite match up in each rotation. See, there's the end of it there. That one's going to come down. It won't match up with where it left initially until it performs some number of cycles. So this rosette motion is part of the Sommerfeld picture. And what it means is that these conserved quantities are not as conserved as they were in the Bohr model. And in particular, I won't go into any details here, but because my thesis, if you remember, was on dynamical symmetries, it was known that the dynamical symmetry of the hydrogen atom is really what's called SO4. It means rotations, special rotations in 4 dimensions. Well, this symmetry gets broken when you make it relativistically invariant, partly because the Runge-Lenz vector is no longer a constant of motion. This is something that Eliezer also pointed out, and this is another reason why he thought this was interesting for me. Now, I need to explain, how do you get this discrete spectrum from the Newtonian model? Just talk about the planetary model. Well, you still have the angular momentum is conserved. And a definition of angular momentum is it's the product of the momentum in any given direction times the orthogonal vector that points towards the center of the system, which in this case is the proton. So it's the orthogonal motion due to the momentum traveling this way and the tendency to want to move towards the center of the system. That creates essentially like a torque, if you will, and that provides a new vector, which is the angular momentum. So depending on how fast the planet or the electron is going around the proton or the sun determines the size, the magnitude of the angular momentum. So P is the linear momentum, R is the distance, the displacement to the electron from the proton. The rule is that you integrate the momentum over the path R, that's the orbital path, and you simply slap on a integer value. That will give you the radial component. That's the radial component of P, because it's, it's moving, it's in an ellipse. And then there's also an angular component, and that's the Sommerfeld, the component that was introduced. This is what's called the Bohr-Sommerfeld quantization rules. This means this is really going on in phase space, and I don't get any real details here, but if you take a very simple model like a mass on a spring, you have Hooke's law, restoring force is equal to the negative displacement of the mass on the spring. The spring tries to pull it back. There's a negative sign there. The spring constant. That's the force. If you take the potential energy, which is the derivative of that thing, you get, sorry, the integral here, you get the potential. So if you took the derivative of the potential, you get the force. So this is squared. It's a parabola. Here's the classical Newtonian potential energy for a mass on a spring. Depending on the spring constant, you can have values of potential energy anywhere in that parabola, but it is a parabola because that's q squared. Q is just a distance. If you take the total energy, that's to say combine the kinetic energy and the potential energy together, then you get this quadratic or symplectic form. And if you plot that in a diagram which has P, the momentum, as one axis, y-axis, and Q, the displacement, as the x-axis, you get an ellipse because it's quadratic bilinear form. So the area in that under that ellipse tells you the amount of energy in the system, basically, is what it boils down to. When you apply these Bohr-Sommerfeld quantization rules, what you're doing is you're actually making the energy not continuous like it is in the Newtonian system, but you're forcing it to be discrete by imposing these quantum numbers here, n and k, multiplied by h bar, which is Planck's constant over 2 pi. So this is the difference. This is classical mechanics on the top. Below is the quantum mechanical version. That's to say discretized energy levels. And in the case of the harmonic oscillator, these are all equally spaced, sometimes called a ladder. Compare that once again with the Coulomb. That's much more complicated, and you see they're not equally spaced. In fact, they converge and become a continuous set of lines. So that's where that's coming from. That's the whole idea behind this form of quantization, but it really is ad hoc. Compare that with what happened in 1924. So quantum mechanics, what I'm going to call quantum mechanics version 1 now. Version 0 is the Bohr-Sommerfeld picture. Version 1, which happened a decade later, and the one that's discussed in, well, it's not actually discussed in Max Born's book, the one that's in the center of the stack, but he wrote a book about this. And what Max Born was doing, he doesn't really get enough credit for what he did. First of all, he really tried to formalize very coherently and very mathematically what Sommerfeld had done. But it's a very well-written book, even in translation. And he also discusses, where it aligns up with experiment and where it doesn't. So he's not just doing the math, but he tries to make the math very rigorous to point out, where the pitfalls are and what needs to be corrected. Now, what's ironic is that Heisenberg had finished his PhD with Sommerfeld and had gone to Göttingen to work, I guess as a postdoc, we would say today, as Born's assistant or postdoc, one of them. Pauli was another one at the same time. And as I was telling Tapesh the other day, it's an interesting story that most people don't know. So at the time, Heisenberg was trying to understand how to quantize a harmonic oscillator like this, mass on a spring, without just using these ad hoc rules of quantizing the phase space, which is what Bohr and Sommerfeld were doing, basically. Sommerfeld, really. And so that's ad hoc. So you take the Newtonian picture and then you sort of glue on these rules, the space-space quantization rules. You glue them on to the side. Heisenberg was trying to do this in a formally consistent way. And he was using the harmonic oscillator as the example. But he couldn't get it to work. And then he came down with a huge bout of hay fever. I suffer from minor hay fever, but nothing like what probably Heisenberg went through. Even I can't think straight when your sinuses get clogged up and everything. I don't know what Heisenberg was going through, but he had to leave Germany. Presumably it was in the summer. He had to leave Germany and go to an island that's off the coast of Denmark called Heligoland. And the reason he went there is because there's no trees and no grass, so there's no pollen. So he went there to recover from hay fever. I think it was a well-known place at that time. And once he started to recover, he was down by the beach and he was looking through his notebook and trying to see if he could crack this problem that he'd been unable to do. In other words, he'd been unable to produce the discrete spectra of the harmonic oscillator, the mass on a spring, in a self-consistent way. In other words, no phase-space quantization. And he simply couldn't get there. And he reached a point of despair where he was about to throw his notebook into the ocean. But just as he was about to do so, he was looking at part of his derivations, and I've just merged these two things together. They don't work like this, but this line represents what he was looking at. He was looking at an equation where on the left-hand side, you had a whole bunch of junk plus a term P times Q. The P and the Q are the same ones that are in the ad hoc phase-space quantization rule. So linear momentum and position on the left-hand side, and then on the right-hand side, a similar, more junk, and a term Q times P. And of course, what he'd done up to this point was these two things are the same, so therefore you would cancel them out and collapse down the result. And he couldn't get there. He got the wrong result. So out of desperation, he decided not to do that. And when he didn't cancel those terms out, he got the spectrum for the mass on the spring that he was looking for. I see Tabash there. You're going to tell me we're out of time?
No, we have 4 more minutes actually.
Oh, good.
But I wanted to see if there are people who want to ask any questions. I mean, I know I find it amazing, but I don't know if other people, how did they find it?
Could we just hold off until I get
Yeah,
to
yeah,
this?
we'll hold off for a few minutes. Yeah.
Welcome questions, but I'm going to try and finish up fairly quickly here anyway. Anyway, the point is that when he didn't do the cancellation, he got the discrete ladder spectrum of the harmonic oscillator. And he went back to Göttingen and he told his boss, Max Born, that he'd managed to get there, and he showed him how he did it. And Max Born's response was, "Congratulations, my boy, you just discovered matrices." And the point being there that matrices were known to mathematicians, and Max Born was trained originally as a mathematician, not a physicist. And he knew about matrices, which were developed in the 19th century, about 100 years before, roughly speaking. Heisenberg was clueless about that stuff. And Born recognized what it was immediately, and very shortly thereafter produced this equation, which is not the same one as Heisenberg. I'm just putting them together for the purposes of making the slide. And this is the equation. So in other words, if you don't cancel them out, normally if P and Q were arithmetic numbers, you would cancel them out because it doesn't matter which order the product is in. If they're matrices, you can't do that in general. The order matters. When you multiply two matrices, it matters which way you do it. So these are actually matrices now, a matrix representation, but they refer to the same thing. They're actually infinite matrices that refer to momentum and position in the same way as Heisenberg meant. And here's the result. Since they're not equal to zero, they're equal to something. Guess what? Planck's constant. So P times Q minus Q times P equals essentially Planck's constant. In other words, something not zero. If it was arithmetic, it would be zero, but they're not. And this is the whole thing. This is not well recognized. This is actually the Born equation, and this Born equation is actually Heisenberg's uncertainty principle, although it wasn't recognized that way at the time, and Heisenberg came up with the idea of the uncertainty principle later. But this is it. This is the point of quantum mechanics. It says in Newtonian mechanics, everything's arithmetic. Therefore, they would cancel. In quantum mechanics, they don't, because they don't commute. What does that mean physically? It means, unlike Newtonian mechanics, you can't measure the momentum accurately and then also measure the position accurately, or vice versa. So the non-commutativity here means you can't simultaneously measure position and momentum. That's the Heisenberg uncertainty principle. You can do it in Newtonian mechanics, but you can't do it in quantum mechanics. And that is, of course, the crux of quantum mechanics. And that equation is on Max Born's tombstone. There it is there. Now, the only thing I need to finish up on here is what on earth is John Travolta doing on this slide? Well, it's not John Travolta, it's this person here. This young lady is Olivia Newton-John, in case you don't recognize her, who comes from Melbourne. And she is the granddaughter of Max Born, number one. Number two, she's recently she died, unfortunately, but she's a few years older than me. And when I was 15, I had a rock band. And ultimately, we ended up working for the same agent in Melbourne. And Olivia Newton-John was a singer. She didn't have a band of her own, and she wasn't part of a band. So the agency would rotate bands to back Olivia Newton-John at whatever gigs were going on in Melbourne. So from time to time, we would back her. So that's my personal connection with Max Born through Olivia Newton-John. I told you it's going to be a personal journey. So let me just quickly move ahead, because if we finish up now, I might have to come back to this in the next session. Here's Eliezer and Dirac. Dirac came to Australia in 1976. Eliezer and I flew to Adelaide to see him. For some reason, Dirac didn't come to Melbourne. I don't know why not. And this is Dirac. He's actually eating a barbecued sausage here, so he's chewing on yet another problem. What's a bit sad about this picture is not obvious, but Eliezer is standing there, and I watched them. You know, I wasn't engaged in conversation, but I was watching him fairly closely. Dirac never really spoke to him. There was no conversation. There's no small talk, and that is Dirac. And I think it was rather unfortunate that Dirac, Eliezer, went all this distance, came to meet him. Obviously, happy to be there, but you looking at it as a casual observer, you think these two didn't even know each other, and yet Eliezer had worked for Dirac in the 1940s. So kind of sad. Very quickly, what did Dirac do? Well, he took the Schrödinger equation. This is now quantum mechanics version 2. Took the Schrödinger equation, which was not relativistically invariant, and made it relativistically invariant. And other people had tried to make a relativistic version of Schrödinger's equation, including Schrödinger. And that's this equation here, today called the Klein-Gordon equation, because Klein and Gordon discovered it separately. But it did not look right. And what Dirac did was, the reason it doesn't look right is you've got, if you look at the Schrödinger equation, you've got second order derivative in position. This is a wave equation, second order derivative in position, first order in time. The Klein-Gordon is second order in position, but second order in time. This didn't look right, and therefore Schrödinger abandoned it. Klein and Gordon went ahead and published it. Schrödinger abandoned it and came up with this equation 7 instead, but of course it's not relativistically invariant. He knew that. Dirac, after all this stuff was published, Dirac found an equation which was first order in time, and also turns out to be first order